The objective of this video is to help you better utilize the ETCAI software to solve the parameters for series, parallel, and complex circuits. We are going to need a few materials to do this. Obviously, we need the software itself. You're going to need an engineering calculator along with Mr. Ryan's engineering notation learning guide. And you're going to need Mr. Hatrock's DC cheat sheet with all of our formulas, rules, and laws on it. So essentially, let's do a quick review of the important laws that we need for this. Obviously, Ohm's law, E equals I times R, and P equals I times E. Two more important things is Kirchhoff's law. Current is constant in a series loop. So whenever we have a series circuit, no matter where you measure that current, it will always be the constant of what we call I total or current total. And then there's Kirchhoff's parallel law, where voltage is constant across a parallel circuit. So whenever we have two or more components in parallel, if we take a meter and measure across those components, we're going to find that the voltage is always the same. With these rules in mind, let's try to tackle our first problem. Now, what I'm going to do is I'm first going to do the easiest. We're going to do a series circuit. Then it'll be followed by a parallel circuit. And then we'll continue on with a complex circuit. So let's look at our first problem. Remember, we need our DC cheat sheet, our engineering notation learning guide, and calculator that does engineering notation. So let's start with the first circuit. Here's a 28.489 volt battery. The positive is the long line, the negative is the short line, and we know that current flows from minus to plus. The high positive voltage on the battery attracts the negative electrons. And the first thing we have to do when solving any circuit parameters is identify the circuit. We need to know, is this a series circuit? Is this a parallel circuit? Or is this a complex circuit? So let's use the software and let's look at this and analyze it. So if we follow the negative electrons, there's only one path. So that's a series circuit or a series loop. It does not branch off and go through other components anywhere else. Think of it as a single lane highway for electrons. So we have current flowing from minus to plus, one single path, creating our series loop. And the one thing that we have to remember, Kirchhoff tells us the current is constant in a series loop. Now, I want to solve current and I want to solve resistance. Without these two parameters, I can't solve the rest of my problems. So let's figure this out. How do we solve for series circuits? Well, if you refer to your DC cheat sheet, you will see that the formula for series resistance is R1 plus 2 plus R3 plus however many resistors there are. If there was 10 resistors in series, we would just add them up. In this case, we have 3 resistors in series. We have 1500, 1200, and 1000. So that should equal 3700 ohms of resistance. I'm going to put that in there. Now, you can check the work as you go. As you see, if we're keeping score, it tells you that it costs us 2 points to check our work. But we're going to check it anyway and say, look at that, we got it right. Okay, so our next parameter, remember I said cover up the unknown or what the teacher or the software is asking for. So we're looking for I. So cover up the I in your Ohm's law pi, and you will see that E over R is what remains. So basically, E is electromotive force measured in volts, and that quantity is right here. So you're going to put 28.489 volts in your calculator, and you're going to divide that by your total resistance of 3,700 ohms, which is also 3.7 K ohms. And that is going to give us a current total of 7.699 milliamps. Let's check it and see if we did it right. Hey, we got 2 in a row. Very good. Now, IR1, IR2, and IR3, we need to solve that. But wait a second, doesn't Kirchhoff tell us the current is constant in a series loop? Meaning if I put an ammeter here, or here, or here, or in between these two resistors, or in between these, or anywhere in this path, that the current is going to be the same as I total. So in this case, we can very simply, using Kirchhoff's law, put in each current value. So we're going to put in 7.699 milliamps, 7.699 milliamps, and 7.699 milliamps. And magically, it's going to tell us it's right. That's why it's a law. Nobody's disproven it, and it always seems to work for us. So let's stick with using it. So current is constant in a series loop. That means anywhere we have a current in that loop, it's going to be the same as I total. So IR1, 2, and 3 are equal to I total. So the next three there were correct. Now, what is VR1? VR1 is the voltage drop. And some books and some software, and when you take the NOCTI and the CET in the future, they're going to call it ER1 because in electronics, the unit is voltage and it's the unit of electromotive force. So they call it E. But in high school physics class, they just call everything V for voltage. So this software uses the nomenclature of VR1, VR2, and VR3. But in the future, you may see it expressed as ER1, ER2, and ER3. So just giving you a heads up that you're going to see it both ways, depending on the textbook, the software, or the test that you are taking. Okay, so if I was to take a voltmeter and measure across R1, I would see some voltage drop. If I take another voltmeter and go across R2, I'm going to see voltage drop, and the same thing for R3. Now, each one of these resistors drops some voltage. Which one would drop the most? Well, the highest resistance. That's the one that opposes current flow the most. So this will drop the most voltage. Which one would drop the least? Well, using that method, we're going to look at this and say the smallest resistance would drop the least. These are very important concepts to understand. Another concept to understand is that the sum of all these voltage drops, Kirchhoff tells us this again, Kirchhoff's voltage law, the sum of all the voltage drops across R1, R2, and R3, if we did our math right, is magically going to add up to 28.489 volts. So how are we going to solve this? Well, again, refer to your cheat sheet and cover up the E because we're looking for ER1 or VR1 as the program's calling it. And E is I times R. So what I are we talking about? Well, we're talking about the current through R1 because we're trying to figure out the voltage across R1. So we know that the current through R1 is 7.699. Don't forget, if you're using an engineering calculator, you have to hit shift for the milli and the little m over to 5 key. So it's 7.699 milliamps. And we're going to multiply that by the resistance of 1500 ohms. So VR1 will be 7.699 milliamps times 1,500 ohms, or 1.5 k ohm. And that is going to give me a voltage drop of 11.548 volts. How do we solve VR2? Exactly the same way. We're going to take 7.699 milliamps, and we are going to multiply that by 1,200 ohms because that's the value of R2. And that's going to give me 9.238 volts. Remember, we go 3 significant digits in electronics. So if there's something after that 8, you can drop it off. Don't round up and don't round down. We typically go 3 significant digits after the decimal. If we round up, it messes up our Kirchhoff's law, and we add them up, and it might put us over this, and we'll be like, ooh, did we do that right? It might end up a little low by dropping, but nonetheless, we never want to go over. Okay, and VR3, again, cover up the E, it's I times R, so it'll be IR3, which is 7.699 milliamps. And we are going to multiply that by 1,000 ohms. And that's going to give me 7.699 volts. Now, remember those concepts I said? Didn't I say the 1,500 ohm resistor was going to drop the most voltage, and that the 1,000 ohm resistor was going to drop the least amount of voltage? And this guy, being somewhere in between, is going to drop somewhere in between. Well, look at that. VR1 is 11.5 volts. VR3 is the lowest at 7.699, and VR2 fell somewhere in between. Also, let's add them up. If I do 11.548 plus VR2, which is 9.238, plus VR3, which is 7.699, that's going to give us 28.485 volts. Well, this is 28.489. Why did it not quite hit that 9? Because we dropped after the third significant digit. So you'll get very close. You may not get exact, but you'll get very close. And since we're never rounding up, you'll never go over. Well, let's check our little thing here. Correct, correct, and correct. Now, power. How do we calculate power? Well, power's easy. Power, cover up the P in the power pi, it's I times E. So basically, it's volts times amps. So this is power total for the whole circuit. That means this battery and all three resistors are consuming power. I'm supplying energy, and this is our load that's consuming power. How many watts of power is it consuming? It's 28.489 volts, and we are going to multiply it by our total current of 7.699 ohms. I'm going to hit equals, and that gives me 219.336 milliwatts. Now, if we did it right, it'll say right, and it does. Now, what I can tell you is, do we agree that resistor 1 consumes some power? Resistor 2 consumes some power, and resistor 3 consumes some power. All three resistors consume power. There's nothing else in the circuit. So basically, whatever power this one, and this one consume should add up to power total. So let's look at this. How do we do PR1? Again, cover up the P in your pi, it's I times E. But in this case, it would be VR1 times IR1. And when we do PR2, it'll be VR2 times IR2. And when we do PR3, it'll be VR3 times IR3. So let's give this a shot. We're going to do 7.699 milliamps, and we're going to multiply that by the voltage drop of 11.548 volts. And that gives me a power total for resistor number 1 of 88.908 milliwatts. Now let's do PR2. Again, it's IR2 times VR2. So it'll be 7.699. Don't forget to hit your shift milli. Multiply that by 9.238 volts. And that will give us our total power across R2 of 71.123 milliwatts. And finally, let's do PR3, which is 7.699 milliamps, and we're going to multiply that by a voltage total of 7.699 volts, giving me a power of 59.274 milliwatts. Let's see if that's right. Check, check, and check. How do we know this is right? We can add these up, and they're going to equal our power total. Now, what I would like you to do is open up the software and practice doing this on your own. Every time you open up the software, it will generate new problems with new numbers. So you want to get series circuits down first. Once you've mastered series circuits, you can move to the second part of the video, which is parallel circuits. So I'll allow you to take some time, practice series circuits, and then we'll move on.